Hi, today we have three problems that we need to prove. So let's proceed with number 1. Show that x over y plus y over z plus z over x equals 1 have no all positive integer solutions. First, we notice if our input x, y, and z are all positive, then the fraction x over y, y over z, and z over x are always positive less than 1, so that their sum will be equal to 1. If these fractions is less than 1, then we can say x over y is less than 1, y over z is less than 1, and z over x is less than 1. The first inequality, by multiplying both sides by y, become x is less than y, and the second, y is less than z, and z is less than x. First and second inequality is same as x is less than y less than z. And we copy the third inequality. So we must have these conditions so that the sum is equal to 1. We notice from the first condition that x must be less than z. But the second condition is exactly the opposite. So we have the contradiction. It means that we cannot have all positive integer solution. So by contradiction, it is proven. So number 1 is done. So second question. Prove that the solutions of the inequality sin x plus y plus z minus 1 is greater than or equal to x squared over 2021 happens if x equals 0. This might look like a difficult question, but actually it's not. By noticing that the sin x plus y plus z is in the range of -1 to 1, any input of sine function always result -1 to 1 only. Now, we deduct both sides by -1, become -2 less than or equal to sin x plus y plus z minus 1 is less than 0. Sin x plus y plus z minus 1 is exactly the left hand side and with a maximum value of 0, and still the right hand side x squared over 2021. Now we notice that x squared over 2021 is always positive or 0. Any input x, when you square, is always give positive. So right hand side have minimum value of 0, while the left hand side maximum value of 0. But the inequality, the left hand side must be greater or equal to the right hand side. Left hand side and right hand side must be both 0. So that is when x equals 0. So basically, y, z, and 2021 is just a decoration. Hence, we only have solution when x equals 0. So our final question, number 3. Show that we have infinitely many solutions for x squared y squared plus z squared minus xy minus xz minus 2yz equals 0. Now, if we can show under a condition, and this condition gives infinitely many solutions, then we can consider this proof as valid. Let's say y equals z, and we set them both equal to a. We substitute a into the original equation, become x squared plus a squared plus a squared minus xa minus 2 times a same as a squared equals 0. A squared plus a squared same as 2a squared minus 2a squared 0, and negative xa minus negative xa same as negative 2ax. and we've got x squared minus 2ax equals 0. So we can factor x, become x times x minus 2a equals 0. The solutions are x equals 0 and x equals 2a. And a could be anything. It could be negative or positive value. So under this condition, y equals z equals a give infinitely many solutions. Hence, our original equality give infinitely many solutions.